Welcome back. In the last video we have seen a time signal, how it is split into different signals of different frequencies, and we represent that time signal as a series, sum of all these linear combination of these signals of different frequencies, which are discrete frequencies. This is called Fourier series, and we will see how this Fourier series converges to the time signal pointwise, under what conditions on f, under what conditions of the function f we have this convergence. We will see before we do that, we prove that result. We will do some more examples. Last we have seen mod x with period -1 period 2 mod x, that is defined on the closed interval -1 to 1. If you repeat it, we extend it over full real line as a periodic function, and we can have a representation for a periodic function f x, which is mod x, as a series, as a Fourier series. We have seen, we just found the Fourier coefficients. We calculate the Fourier coefficients and put it as a series. That series we are calling as a Fourier series. We will just start with in this video we will have few more examples. The advantage of this Fourier series is that we can also get the value of some series we can find from the Fourier series. We will see how. We will take this example. There is a function, the time signal is that f of x is x times let us say 2L minus x. So, this function, let us take a function like this, and where is it defined? It is defined everywhere actually. If you see, it is just a polynomial, it is actually defined on a full real line, but we will take it as a periodic function with period 2L. So, you can say that it is defined over 0 to 2L. So, if you view this as a function which is periodic over a real line, it is going to be 0 to 2L and 2L to 4L, and similarly 0 to minus 2L and so on. You can have a representation. So, you have whatever be the function that is going to be defined here. If this function f is this here, f is over here, so it is going to be repeated everywhere, here and here, everywhere. Okay. So, you can extend like any function defined on a finite interval, you can extend it over full real line as a periodic function. So, if you consider this, so what is Fourier series? So, this consider this as a time signal. We can break this into different frequencies, and we have defined in the last video what are the Fourier coefficients with period 2 period, the Fourier coefficient of a time signal f of x with period L. So, here we have a function that's that is a function that's a function with time that's period 2L. So, what are the Fourier coefficients? Fourier coefficients in this case. So, let us define. So, they are 2 divided by, so its period is L. So, earlier, so now we have a period is 2L. So, you have 2L, this is from 0 to 2L, and this function f x cos n omega naught x dx. What is omega naught? Omega naught is 2 pi by L, which is here 2L, the period is 2L. So, which is pi by L. So, you have 1 by L 0 to 2L f x cos n pi x by L dx. This is my a n, which is running from n is from 0, 1, 2, 3 and so on. So, that has a 0 as well. So, similarly, other coefficient b n, which is 1 by L 0 to 2L f x, instead of cosine now you have sines, sin n pi x by L dx, n is running from 0, 1 to 3 onwards. So, we will see, we will just calculate these functions, these Fourier coefficients for the function x into 2L minus x. So, what is start with a n? We can have a 0 first. A 0 is 1 by L integral 0 to 2L f x is x 2L minus x n equal to 0, cosine value is 1. So, you have dx, this is going to be x square L by 2. So, that is 2 goes x square minus x cube by 3, that is the antiderivative, and we have 1 by L. If you substitute these limits, what you get is L goes x square. So, 4 L square, and then this one minus L square, actually 8 L cube, that is, and you, if it goes with 1 L. So, you have 8 L square by 3. So, it is equal to 4 times 1 minus 3. So, what is this value? So, 4 L square comes out, you have 1 minus 2 by 3. This is equal to 4 by 3 L square. So, A naught we found as this. Now, we can calculate any A n is running from 1 to onwards. So, 1 by L 0 to 2 L f x cos n pi x by L dx, n is running from 1 to 3 onwards. We do integration by parts here. So, 1 by L you have sin n pi x by L divided by n pi by L, this, and then for which you have 0 to 2 L limits minus L by n pi integral 0 to 2 L sin n pi x by L. Then you have to differentiate this f x, which is x into 2 L, that is 2 L minus 2 x. So, you have 2 L minus 2 x is the derivative of f, which is dx. So, if you calculate, so L goes here and also goes here. So, what you get is sine function. When you substitute x by 2 L, L goes 2 n pi, sin n pi is 0, and sin 0 is 0. So, this is completely 0. So, you have again, if you do one more time integration by parts, 1 divided by n pi, now L by n square pi square into, now you have cos n pi x by L, for which you have 0 to 2 L minus minus plus, and you have cosine is minus. So, the here it's, so you have a minus here. So, minus cos n pi x by L divided by n pi by L. So, L divided by n pi comes out, this is already plus here, and this is going to be minus minus plus, and again one more minus comes in here. So, you have minus L by n square pi square integral 0 to 2 L cos n pi x by L. Of course, I think I missed f x here. So, f x here, and you have here f dash x, which is L into 2 L minus 2 x. So, for which you have this limits. Okay. And here if you differentiate this one, this is your f x now. So, you get minus 2. So, it is going to be plus 2 L dx. So, here now if you can see here 2 L minus x, L minus 2 L minus 2 L is going to be 0 cosine, and also what you have, and you put x equal to 0. So, you get 2 L square divided by n square pi square, cos 0 is 1. Okay. So, here 2 L minus 2 x, no, that is not 0. So, 2 L minus 2 x, 2 L, L minus 2 L, that is going to be minus L. So, minus L square divided by n square pi square cos 2 n pi, that is 1, minus cos 0 is 1. So, here 2 L square divided by n square pi square. So, together it is minus 4 L square by n square pi square. That is what you get. You have this term, and here you get 2 L by n square pi square. We have antiderivative is sin n pi x by L divided by L by n pi. So, divided by n pi by L, that is L by n pi, for which you put the limits 2 pi 2 L. So, this is the final result for A, and so this is equal to minus 4 L square by n square pi square plus 4 L square by n square pi square. So, here n cube pi cube, and sin L L goes 2 n pi. So, that is 0. So, actually this is 0. So, nothing, no contribution here. So, this is exactly what you get for A n's. For A n's, is non-zero here. Similarly, you can find B n's. So, B n's are, so instead of cosine, you have sine here. That is the only replacement. So, let us work out what is this B n. B n is 1 by L, 0 to 2 L, f x times sin n pi x by L dx, n is running from 1 to 3 onwards. So, if you do the integration by parts twice, you have 1 by L f x minus of this cos n pi x by L divided by n pi by L. This L L goes minus minus plus integral 0 to 2 L, and you have 1 by n pi L by n pi, but L L goes again with the outside L, and this is sin n pi x by L into f dash, that is 2 L minus 2 x, 2 L minus 2 x with sin. This is what it is. So, this is equal to, now here when you put a 2 L, cos function will give you 1, cos 2 L, cos this function, cos function will give you 2 L, that is 1. So, you have minus x into, so basically what you have, what is f? 2 L x minus x square. So, 2 L x minus x square. So, 2 L x, so you can write here 2 L x minus x square is my f x. So, f at 2 L is actually equal to 4 L square minus 4 L square, 0. Yeah, so 0. So, f at 2 L is 0, and f at 0 is what? If you put 0, that is also 0. So, you have this contribution is 0. So, finally, what you end up is 1 by n pi. Again, for this integral, if you do the integration by parts, 2 L minus 2 x, sorry, this is cos, right? So, this is cos. So, you have a sin n pi x by L by n pi by L into, for which you have 0 to 2 L, and you have minus L by n pi integral 0 to 2 L sin n pi x by L into, differentiate to this 2 L by 2 x, so that will give you minus 2. So, it is going to be plus 2 dx. So, together again now sin will give you at 2 L and 0 is 0. So, this will be 0, and you have here, so 2 L by n square pi square, this will be minus cos n pi x by L into L by n pi, for which if you apply limits, what you get is 2 L by n square pi square, 2 L cos n pi x by L will be 1 minus L by n pi take it out. So, you get minus L square n cube pi cube, and you have left with only for cosine. Cosine will be minus, that is also 0, okay, 1 minus 1 which is 0. So, b n's are 0, you get only a n's, and a naught is non-zero, 4 by 3 L square a naught and a n. So, implies if you assume the Fourier series, if you assume a result that any time signal sufficiently good time signal, if you can split it into time signal of different discrete frequencies, you can take a linear combination of all these, and then you can say that this is actually equal to your time signal. So, we will see that is a Fourier series of this function f x is. So, we can write this, so which is 2L x, 2L minus 2x, 2L minus x into x. So, this is your time signal, which is a naught by 2. So, what is the value of a naught which we found? 4 by 3 L square. So, 2 by 3 L square is a naught by 2, 2 by 3 L square, that is a naught by 2 plus b naught is 0, and you have a sigma n is from 1 to infinity. A n is minus 4 L square by n square pi square cosine cos n. What is your omega naught fundamental frequency, which is pi by L. So, pi by L n pi by L x omega x. Okay. So, this is exactly your Fourier series. So, minus you can take it and put it outside. So, this is your Fourier series. So, you actually assume that this Fourier series converges to the signal. So, that is why we equate it here. So, this is still actually question mark unless we prove that this actually converges pointwise. You fix your x, this series converges to this function 2Lx minus a 2Lx minus x into x. If this converges, so we are only assuming as of now, if you calculate like this, you get your Fourier series that actually converges to the some function f when it is this function is differentiable, smooth piecewise differentiable function. You can easily say that, okay, that will actually prove the result. So, we are only just calculating this right side, and we say that this is actually still in the question mark, actually true. And see, once you assume that it is the Fourier series, so you have this is the Fourier series of this function. Now, what can we say? So, what is this Fourier series? So, this is equal to, you can write 2 by 3 L square minus 4 L square by pi square. If you take it out, and what you get is a series n is from 1 to infinity 1 by n square. So, cosine cos n pi by L x divided by n pi x by L divided by n square. So, this is what it is, 2L minus x into x. So, what do you get? So, if we put x equal to 0, so where is x? X is between 0 to 2L. So, we will put x equal to 0. So, putting x equal to 0 will give me left hand side is 0. So, you will get 2 by 3 L square, which is equal to minus 4 by 4 L square by pi square into the sum n is from 1 to infinity. Cosine function at 0 is 1. So, 1 by n square cosine cos 0. So, it is this. So, this will give me sigma 1 by n square, the well known result 1 to infinity, which is equal to 2 by 3 L square into pi square by 4. So, 2 goes. So, what you get is pi square by 6. So, you get this pi square by 6, this is a well known result. Okay. So, Fourier series, once you calculate the Fourier series, you try to fix your x value, that will give you some series. If the series so happens to be a well known series, you will know the sum of its sum of the values, sum of that number series, that is that series value you will get it as from the Fourier series, but it is not the other way. So, you give your own number series, and it is difficult to find a suitable function f for which the Fourier series will give you once you fix the x value, the series, the number series you have given. Okay. So that is not the other, so other way. So you do your Fourier series, so that will give you, that will generate, once you fix x value, that will give you some number series. That number series value, sum of that number series, you know the value. So here, so this is the well known result, and also you can also get one more here. So by putting x equal to L, if you put x equal to L, what happens? So you get left hand side L square, which is equal to 2 by 3 L square minus 4 L square by pi square, and you have n is from 1 to infinity. Cosine of n pi, put x equal to L, cosine of n pi, which is minus 1 power n divided by n square. So put n equal to 1, right, cos pi, that is cos pi is minus 1, and so on. Yeah. So if you remove this one, so you have a minus 1 and you put 1 here. So you will get, just leave it here. So this will give me L square cancels, and you get this series, the value of this series, n is from 1 to infinity, minus 1 power n by n square is equal to 2 by 3 times pi square by 4. Is this correct? Cos n pi. Yeah. So this is also a value is same. So you get pi square by 6 minus 1 power n by n square, which is equal to pi square by 4. Yeah, that's correct. So you get pi square by 6. Something is wrong. L square. Oh yeah, this is a mistake. So this mistake is here. So this is equal to minus of this. Okay, so let me do it carefully. So 4 by pi square minus 4 by pi square equal to 1 minus 2 by 3. This is 3, 1 by 3. So this will give me a sigma minus sigma n is from 1 to infinity minus 1 power n by n square, which is equal to pi square by 3 into 4. Okay, so this is equal to pi square by 12. Okay. So this is well known result when you put x equal to 0, and you have this result now. So this will give you as n equal to 1, this is minus 1 by 1 square. So it is going to be 1. So it is going to be 1 1 minus minus plus. So 1 minus or divided by 1 by 1 square plus minus 1 by 2 square plus 1 by 3 square minus 1 by 4 square, and so on. Whose value is actually pi square by 12. So this is the result you get. This is also well known. Okay. So this is how you can get the results. You can get the sum of the number series from the Fourier series. We will do example, one more example. We will try to calculate the Fourier coefficients and the Fourier series for a given function, and then out of that we will try to get the sum of the series. So here we choose the another example, which is a function is something like this, some constant k and a function x. K is actually between minus 1 to 0, and then here this is between 0 x less than 1. So if I have like this is a piecewise function. You can see from minus 1 to 1, minus 1 to 0, this is a constant function k, let us say 1. If k is 1, it is like this, and if it is between 0 to 1, it is going to be like this. So you can always extend this function over a full real line like this, and this go on like this. You can go on. So you can extend both sides like that as a function over a full real line, but it is with the period. So it is same thing, pattern is repeated over an interval of length 2. So the period is 2. So this is a piecewise periodic function. Fx is a piecewise function, piecewise continuous function with period 2. Okay. So let us see the coefficients Fourier coefficients, which is what are the Fourier coefficients in this case? The period is 2. So, you have 2 by L, L is the period. So, AL, AN, which is 2 by L is 2, L equal to 2. So, integral this is from -1 to 1, because this is from -1 to 0, -1 to 1. The function is defined f x, this function cos n omega naught, that is the fundamental frequency is 2 pi by L, L is here 2. So, it is pi. So, cos n pi x dx. So, this is your a n's. B n's are similarly, so 2 by 2 is 1. So, B n's are similarly you can define f x, instead of cosine you have sine there, n pi x dx. So, this is running from n is from 1 to 3 onwards. So, n is also 0 here. So, both if you define at n is equal to 0, 1 to 3 and b 0 anyway 0. So, let us calculate what is this a n. So, a n equal to, so if you calculate, so you have -1 to 1 k is a constant, and you have cos n pi x dx -1 to 0, -1 to 0 is this value, plus 0 to 1, and you have x cos n pi x dx. That is my a n. N is running from 0, 1 to 3 onwards. If it is 0, so n equal to 0 if you put, so let us start with a0. a0 is cos 0, and you put n equal to 0, cos 0 is 1. So, it is 1 integral. So, k times 0 minus 1, so it is 1, k 1, k plus, and here is simply when you put n equal to 0, this is x square by 2, so it is half. So, this is your a naught. So, a n is running from 1 to onwards, so that we calculate here. So, if you do this sine function n pi x divided by n pi, that is antiderivative, k is outside, so it is between -1 to 0. So, this is anyway 0 for n is equal to 1 to 3 onwards. 1 to 3 onwards, because 1 by n we are dividing, we have to make sure that is non-zero. So, this is 0 anyway. So, this contribution is 0 minus yeah, that is gone. So, the other integral plus, now we do the integration by parts here. So, again, so sin n pi x, x into sin n pi x divided by n pi between 0 to 1. So, again contribution is 0 minus, now you have this integral 1 by n pi integral 0 to 1. So, sin n pi x, the derivative of x is 1. So, that is what it is. So, you have minus 1 by n pi. Now, this is minus, so antiderivative is minus cos n pi. So, n square pi square minus cos n pi x by n pi. So, that n pi, this outside n pi will become plus, this minus minus plus. So, you have cos n pi x, this is between 0 to 1. So, you see that this is cos n pi minus cos 0. So, what you get is 1 by n square pi square minus 1 power n, that is cos n pi minus 1. So, this is what you have, n is running from 1 to 3 onwards. So, this is my a n. Similarly, you can calculate your b n, which is k times minus 1 to 0. Instead of cosines, we take the sines, and then plus 0 to 1 x times sin n pi x dx. N is from 1 to 3 onwards. So, this is equal to k times minus cos n pi x by n pi, that is the antiderivative, for which you apply 1 to minus 1 0, and you have a minus minus plus. Okay, that is the simple integral. So, that is the derivative, that is the first integral. Here you do the integration by parts for this integral, second part, second integral. So, you have again minus x cos n pi x by n pi for which you apply minus 1 to 0 limits, and this minus minus plus, and you have this integral 0 to 1 cos n pi x by n pi, and the derivative of x is 1. So, you have this. So, this will be cos 0 is minus 1 k by n pi, you get cos 0 is minus 1, and you have cos minus minus plus cos minus n pi, that is cos n pi, that is minus 1 power n. This is what you get, plus, and here again minus x. So, x is 0, that is 0, and cos n pi. So, what you get is minus minus plus 1 by n pi, and value at cos n pi minus 1. So, that is cos n pi, that is going to be minus 1 power n, okay, plus, and this is sin n pi x by n square pi square between 0 to 1. So, this is because of sin n pi minus sin 0. So, this is anyway 0, contribution is 0. So, you get finally what you get is minus k by n pi plus minus 1 power n by n pi into k here plus 1. This is what is your Bn. So, An is this, and you have Bn is this, and with A naught being k plus half. So, what is your Fourier series? Function f, which is piecewise function, which is k between minus 1 to 0 and x between 0 to 1. So, this function I can write now as a Fourier series k plus half. A naught by 2 is k plus half, k plus half is 2k plus 1 by 2, that is A naught, into 2 divided by 2. So, you have 4, okay, plus sigma n is from 1 to infinity a n's. Now, I use this a n's 1 by n square pi square minus 1 power n minus 1, that is what is my a n, into cos n pi x, fundamental signals, cos n pi x plus now Bn is this, Bn's are minus 1 power n k plus 1 by n pi minus k by n pi. This is my Bn into sin n pi x. So, this is my Fourier series. This is the Fourier series for a piecewise continuous function f x, which is like this, which looks like this if you draw, which you can break. This such a signal, if you have a signal like this, if it repeats like this, you can break this into frequencies, fundamental signals of frequency, discrete frequency 1, 2, 3 and so on. Okay. As you see, frequency, fundamental frequency is here is simply w pi. So, the fundamental time period is fundamental frequency is basically this is the fundamental frequency, so it is pi. Okay. So, pi n's, you will get pi n's. So, n pi are fundamental frequencies, different frequencies. So, you have a discrete signal. Okay. So, this also, if once you fix x equal to 0, for example here, okay. So, you can fix x equal to 0 or some other value, or maybe x equal to half. Okay. So, just want to give you some remark here. So, this function is defined over minus 1 to 1, of course here. So, you can include the endpoints minus 1 and plus 1. Okay. So, here and here. So, this is the closed interval, and at 0 this function is actually discontinuous. Okay. So, one is a k value, other one is actually 0, it starts at 0. Okay. If you take the limit as x goes to 0 from the left side, it is actually 0 here. If you take the limit this side as x goes to 0, function value is actually a k. If k is 0, it is continuous function. If k is 0, what you get is this is the function, continuous function. Of course, it is not differentiable, it is not differentiable, and it is only continuous function. If k is non-zero, so you will have continuous, you have piecewise continuous function up to here, and up to here a continuous function x. So, it is not exactly defined. So, we will see exactly where this at this value what is the Fourier series is this. Okay. So, we can say as of now x is between -1 to so I have not said that this is the Fourier series at 0. Okay. So, we are only just as of now we are only believing that Fourier series by construction from the Fourier coefficients, whatever you get that series that converges to the function f(x) wherever it is continuous as of now, where at the discontinuous points it actually converges to the value of function, average value of the function from both sides. So, if you actually see this function, once you fix x equal to 0, we will prove this as a theorem and then maybe in the next video. When you put x equal to 0, what is the value of f(x), f at left side f0 minus, that is actually a k, f at 0 plus, which is anyway x, so that is 0. So, its average value f of 0 plus f of 0 minus divided by 2. So, this is k by 2. So, this is the value you will this Fourier series converges when you put x equal to 0. Okay. The Fourier series constructed by the Fourier's coefficients, it converges to the function whenever it is a continuous at a points of continuity, it actually converges to the function f(x) at the piecewise jump discontinuities at which the average value from both sides your limit exists. So, the average value it converges. This is what we will see. We will prove that in the next video. Thank you very much.